Before we get into section 9.10, Taylor and Maclaurin series, here are the power series for elementary functions, expanded, as well as their interval of convergence. You might want to take a minute and pause this video to copy some of these down, or to take a screenshot of this. We're going to get into section 9.10, Taylor and Maclaurin series. A definition of the Taylor-Maclaurin series. If a function f has derivatives of all orders at x equals c, then the series is as follows, is called the Taylor series for f of x centered at c. Moreover, if c equals 0, then the series is a Maclaurin series for f. We did this, but cut off, so when we call it a Taylor polynomial. With a series, we don't cut it off. This is a series because it goes on forever. It's the same thing. You take the derivative and divide by the factorial. You just need to remember Maclaurin is centered at 0. Theorem 9.22 of a convergent power series. If f is represented by a power series, as shown here, for all x in an open interval, I contained in C, then our series, f to some derivative of c divided by n factorial, and you would have this here. This is equal to a function. We're going to skip example 1 to show that Maclaurin series for sine x converges to sine x for all x, because we won't ever have to justify anything like this, and the process takes a long time. And we already found the Maclaurin series for sine x. So let's look at the guidelines for finding a Taylor series. 1, differentiate f of x several times and evaluate each derivative at c. Try to recognize a pattern in these numbers. So you take a derivative, you find a formula. Then we use the sequences developed in the first step to form the Taylor coefficients and determine the interval of convergence for the resultant power series. So you plug into some formula and you simplify. Within this interval of convergence, determine whether or not the series converges to f of x. For this one, you will have to do this. So let's revisit operations with power series. So when we do this, if we're coming up with a rule or any patterns, we're not going to simplify factorials, okay? So find the Maclaurin series for f of x equals sine x squared. So with this, we can't take derivatives. We can take derivatives, but it's messy in a lot of terms. Usually the College Board likes us to do comparisons. So we know the series for sine x. Okay, so we know the series for sine x, so we're going to go ahead and write that down. And sine x is x minus 1/3, or 1 over 3 factorial, x cubed, plus 1 over 5 factorial, x to the 5th, minus 1 over 7 factorial, x to the 7th, plus, and this equals negative 1 to the n times x to the 2n plus 1, all over 2n plus 1 factorial. Okay, so now what we're going to do is we're going to plug in x squared for x for the composition, because this is for f of x equals x squared. So we're going to find sine x squared. So with our first step, we're going to have x squared minus 1, or x squared to the 3rd over 3 factorial, plus x squared to the 5th over 5 factorial, minus x squared to the 7th over 7 factorial. plus dot, dot, dot. And then we're going to simplify that. So we have x squared minus x to the 6th over 3 factorial plus x to the 10th over 5 factorial minus x to the 14th over 7 factorial plus dot, dot, dot. So with this, we would go ahead and try to come up with a rule. If we use derivatives for this, it would take a really long time. So that's why you want to try to find the composition within a function that we have. So this would then equal, you would want to find some rule, and it's negative 1 to the n times x squared to the 2n plus 1 all over 2n plus 1 factorial. Because all we did is we plugged in x squared. And then that simplifies to negative 1 to the n times x to the 4 n plus 2 all over 2n plus 1 factorial. And they usually do ask for a rule or general term. So we just found the Maclaurin series for f of x equals sine x squared. And usually with these, it's easier if you use a series that you have and find that composition. Let's look at example 3. Multiplication and division. Find the first 3 non-zero terms in the Maclaurin series, f of x equals e to the x, arctan x. Well, same thing. We here, this would take forever because we'd have to use the product rule or quotient rule. And so we know the series for e to the x and the inverse tangent of x. So that's the first thing we would do. We would write down the first 3 or 4 non-zero terms. So for e to the x, it would be 1 plus x squared over 2 plus x cubed over 3 plus, and it goes on forever. For the inverse tangent of x, we would have x minus x cubed over 3 plus x to the 5th over 5 minus dot, dot, dot. So one thing that I want to point out here, when they say the first 3 non-zero terms, that means they want the linear, squared, and cubed. So here, what we're going to do, since it's e to the x times arctangent x, we're going to multiply these two together. So we would write 1 plus x squared over 2 plus x cubed over 3 plus dot, dot, dot. Hopefully we don't have to go further than that, which we don't because it does say cubed, times x minus x cubed over 3 plus x to the 5th over 5 plus dot, dot, dot. Okay, so what we would do is we would take 1 and multiply it by these two. I know I don't have to multiply 1 by x to the 5th because I don't need my 5th power term. So here you would have x minus x cubed over 3. Then, and we'll just do it for the sake of this, multiply it by x to the 5th over 5. So I have plus x to the 5th over 5. Then I would take x and multiply that through, and I would have plus x squared minus x to the 4th over 3 plus x to the 6th over 5. And then I would take my next term and multiply that through and get plus x cubed over 2 minus x to the 4th over 3. Or excuse me, x to the 5th over 3. Over 6, sorry, x to the 5th over 6. plus x to the 7th over 10. So here, I can stop there. I know I don't need my x to the 7th term, 5th, 6th, 4th, or 5th. I only need these terms here because anything over that is going to be larger than x cubed. So my first three terms would be x plus x squared. And then I have two x cubed terms, so I need to get a common denominator, and that would be minus 2x cubed over 6 plus 3x cubed over 6. So that would give me plus x cubed over 6. And that would be my first three non-zero terms. Sometimes they'll ask you for the coefficient of the x cubed term, so you want to make sure you simplify. So if they asked for the coefficient of the x cubed term, you would give your answer of 1/6, and you see that a lot on the exam. Now find the first three non-zero terms of the Maclaurin series for f of x equals tan x. Well, we don't know tan x. However, we do know that tangent x equals sine x over cosine x. If I were to go ahead and do the derivatives of tangent, this would keep going on forever and be really messy. So we're going to skip finding the derivatives and we're going to try polynomial long division. So what we need to do here is first list our terms of sine x and cosine x. The sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot, dot, dot. And then cosine x would be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus dot, dot, dot. So we want to go ahead and divide this, and we want the first three non-zero terms. So we just need to list the first three terms of each of these. So when I divide this, I'd have 1 minus x squared over 2 plus x to the 4th over 24. And then inside I'd have x minus x cubed over 6 plus x to the 5th over 120. So here, x divided by 1 is x. I would go ahead and multiply through, and I get x minus x cubed over 2 plus x to the 5th over 24. Subtract this entire thing out, and you would get x cubed over 3 minus x to the 5th over 30. Then here, x cubed over 3 divided by 1 would be minus x cubed over 3. Multiply that through. And I get x cubed over 3 plus x to the 5th over 6 minus x to the 7th over 24. So then I go ahead and subtract these out. And I get 2x to the 5th over 15. And I won't need to worry about subtracting this out because I know that this will be plus 2x to the 5th over 15. This is really painful And you usually don't see something this painful, but the first three non-zero terms would be x minus x cubed over 3 plus 2x to the 5th over 15. So let's look at example 5. Find the first three non-zero terms in the Maclaurin series, f of x equals sine squared x. So we need to remember that this equals sine x times sine x. And we know that our series of sine x is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus dot, dot, dot. So if I want to find the first three non-zero terms, I have to just multiply this together twice. So sine squared x would be x minus x cubed over 3 factorial, which is actually 6, plus x to the 5th over 5 factorial, which is 120, times x minus x cubed over 6 plus x to the 5th over 120. So we would go ahead and multiply that out, and we would get x squared minus x to the 4th over 6 plus x to the 6th over 120 minus x to the 4th over 6 plus x to the 9th over 36, or x to the 6th over 36. Minus x to the 8th over 720. Then I'd multiply x to the 5th over 120 to each of these, so I'd have plus x to the 6th over 120 minus x to the 8th over 720. And I know it's the first three non-zero terms, so I can stop there because I have 2, 4, and 6. X to the 8th is not going to be included in these. And as I keep going, my power is just going to get larger. So now I add like terms together, and I would get x squared minus x to the 4th over 3 plus 2x to the 6th over 45 for my first three non-zero terms. And example 6, approximate e to the negative x squared from 0 to 1, correct to the nearest hundredth. So when we're doing this, we're going to look at the terms and look at the denominator to see which one's the nearest hundredth with this. So first, let's start with e to the x because we're doing e to the negative x squared. So e to the x would be 1 plus x squared over 2 plus x cubed over 6. And we're looking for an error less than 1 over 100. So now we need to look at e to the negative x squared. We would have 1, then minus x squared, plus x to the 4th over 2, minus x to the 6th over 6. And now we want to integrate term by term. So I'm going to integrate each one of these terms. So I'd have x minus x cubed over 3 plus x to the 5th over 10 minus x to the 7th over 42. And if I were to do the next one term by term, I would get plus x to the 9th over 216. And 1 over 216 is less than 1 over 100. So I would stop there because my next term would be the error. We want less than that. So now you need to plug in just the upper bound, because if I plugged in the lower bound 0, that would just give me 0. So I'd have 1 minus 1/3 plus 1/10 minus 1 over 42, which is about 0.743. So my error would be the 0.743, which is less than so for this, the absolute value 0,1 of e to the negative x squared dx minus 0.743 is less than or equal to negative or to 1 over 216, which is less than 1 over 100. And that's just the notation you are to write it in. So let's look at our quick quiz for section 9.10. The Taylor series for the natural log of x is centered at x equals 1 and is given here. Let f be the function given by the sum of the first 3 non-zero terms of the series. If x is within 0.6 of 1, then what is the maximum error? So try this on your own by pausing the video. And the correct answer is D, 0.032.